Hello everyone and welcome to lecture series for the course FPED, Food Processing Equipment Design. So in previous lecture we have seen how to design a pressure vessel and pipeline system. So in this lecture we will see how to design storage tank. Although the basic design for a storage tank is very much similar to pressure vessel, but there are a little bit difference between a pressure vessel design and a storage tank design. So let's see how to design a storage tank. So the video which is playing on your screens are related to construction of storage tanks. Storage tanks are basically used for storing the grains or storing the fluid or juices or milk. So in food industry, these storage tanks are also known as bulk silos or silos. Sometimes in juice industry we call it as milk silos in dairy industry and juice silos in juice industry. But in grain industry we call them only silos. So let's start it. Let's start the lecture. So in this lecture we will see about storage tanks. What are the storage tanks? Then design of storage tank or silo. Then great pressure theories for designing of silos or storage tanks. After that we will see shallow bin design and then deep bin design. So after that we will see some numericals. So what do you mean by storage tank or silo? So storage tank or silo are the structure which are used to keep the bulk products safe. Like when we are going to store the product in very bulk, like in huge quantity, then in that time we use these silos or storage tanks. So there are different types of storage tanks. Like if we see, so there are different types of storage tanks or silos. So first one is flat bottom silo. As the name indicates, what do you mean by flat bottom silo? As the name indicates that this silo will be flat from the bottom. So this is the picture we are seeing here. This one is about flat bottom silo. The next is hopper bottom silo. Like we know hopper shape. Okay. So here in this picture we will see this is hopper bottom silo. The next is smooth wall silo. So as the name indicates, the wall from the inside as well outside will be very smooth in this case of silos. So smooth wall silo will be very shiny. So this is a smooth wall silo. So from inside also it will be very smooth and from outside also it will be very smooth. So these are generally used for storage of like juices, milk, because if the silo is having corrugated shape, then there are chances of there are problem in cleaning the silos. So hence this type of silos are used in milk industry mostly. The next one is corrugated steel silo. So corrugated steel silos are the silos which is having corrugation on it, like undulation on it. So these are the corrugated steel silos. Bolted, and next comes the bolted and welded steel silo. So this picture we are seeing is bolted and welded steel silo. This type of silos are having bolts or welded on the bolts. So in the figure here, let me go back. Here, here we can see these are the bolts and these are the bolts welded on silo. So this is bolted and welded silo. After bolted and welded silo, the next type of silo is elevated silo. So as the name indicates, this type of silos will be elevated from surface, a little bit up from surface, because it, like when we are storing some cranes, we should have some provision to unload the silo. So these type of silos are used mostly in grain storage, and there will be this type of hopper down, which will be having elevated from the ground level. Here we can see in this picture. The next one is tower silos. Tower silos will be very long in shape, is very long in size. So as the you can figure that, you can see that a tower silo is how much bigger than the car. You can see. So tower silos are very much big in size. Next comes the transportable silos. Transportable silos are the silos which can transport from one place to another. So these silos are having tires, okay, at the bottom of it, so that transportation will be easy. Then the last one will be lip silos. So lip silos is a continuous roll of steel. With the help of this steel roll, the lip silos are formed. So it will be a continuous whole silo, okay, whole strip which will be welded, and it is a form lip silo. So we have seen the different types of storage tanks and silos. The next one is design of storage tanks. So before seeing the design of storage tanks, let me have the pointer. The next is design of storage tank and silo. So before seeing the design of storage tank and silo, we should know some basic terms. The first term is bulk density. We donated bulk density is with rho B. The next term is apparent density, that is rho A. The next is true density, that is rho T. Okay, so what are these densities? So suppose this figure here, we can see this is the three phase diagram of any material. Okay, so if we consider any material, it will having three phases. First one, solid, liquid, and gases or air. Okay, so this solid is having some weight. We will as we know that we denote this weight as Ws for solid. For weight for water, we denote it Ww, and Wa will be the weight of air. Okay, inside a matrix of material. So then let W, capital W, will be the weight of whole matrix. So similarly here we will deal with the volume. Wa is the volume of air. W is the volume of water, and Vs volume of solid. So we know that what are these stands for. Now let's define density. Density is nothing but mass by volume. Correct? Density is nothing but mass by volume. So what do you mean by bulk density? Bulk density is nothing but total weight of material divided by total volume of material. Let V will be the total volume of material. Okay, so V equals to here, V equals to volume of air plus volume of water plus volume of solid. Okay, that will be the V. And similarly W will be weight of air, weight of water, weight of solid. Okay, so this will be the bulk density of any material. Now let's talk about apparent density. What is rho A? In case of apparent density, upper value will be same, weight of whole material divided by weight volume of solid plus volume of water. So here in case of apparent density, we will not take this volume of air, we will take up to here, okay, in case of apparent density. So volume of water plus volume of solid. How we find out apparent density? When to find out apparent density, what we will do, we will tap our material. First we will fill our material in a jar, then we will tap it so that all the void space because of air will come, like air will diffuse out from the material. Okay, that's how we find out apparent density. The last one is true density. Okay, true density is nothing but weight of whole material divided by weight volume of solid only. Okay, so here we remove water also. First we dry the material completely and then we'll tap it so that air will also get away, and then lastly we'll find out the solid volume and divided by the initial weight of the material, that is true volume. Okay, so which one will be the highest one, biggest one? So any idea? Okay, if we consider, so as our denominator is decreasing, so the biggest one will be the true volume, then apparent volume, then bulk volume for one material. Okay, so this is the relationship between the true density, bulk density and apparent density. Okay, so after densities comes external friction. Let me clear everything first. So next is external friction. What do you mean by external friction? External friction is the friction between the particle and any external material, any external surface. For example, this is the ground surface, okay, and this is our material M. Okay, so what will be the friction offered by this surface on this material will be the external friction. Okay, then what do you mean by internal friction? Suppose we are having a layer of material M and above that we are having another layer of material M. Okay, now in this case the friction offered by this first layer upon the second layer is the internal friction of any metal. Then what do you mean by angle of internal friction? Okay, when we increase the angle at certain angle, this upper layer will start moving. Okay, and that angle, when this upper layer will start moving from previous layer, that is the angle of internal friction. Here theta will be the angle of internal friction. Okay, angle of internal friction. Then what do you mean by coefficient of friction? The coefficient of friction denoted by mu, which is equals to force by any particle by force of pull offered on any particle divided by the force due to gravity. Suppose we are having a particle on a slant surface. So this particle will feel some force F, okay, so that it will slide, and there will be another force due to its weight, okay, which is due to gravity, okay, that is in newtons. So F, this F by N will give you the coefficient of internal friction. So we should know all these equations, all these terminologies before we are going to design storage tank, because all these terminologies will be helpful in designing the storage tank. So next is design of storage tank. Here we can see a storage tank. Which type of storage tank it is? Yes, it is hopper bottom silo. So because hopper is there at the bottom, that's why hopper bottom silo. So we can see here that which type of pressure or which type of forces we should consider when we are going to design a silo. So first one is horizontal or lateral thrust or horizontal or lateral pressure. Second one is vertical pressure. So what do you mean by horizontal or lateral pressure? The pressure exerted by the grains when they are filled inside the silo, and it will be in this opposite direction on the walls of silo. Okay, so that silo will fail in this direction. So this is known as lateral pressure divided by PL. What do you mean by vertical pressure? Vertical pressure is in this direction because of gravity, because of the weight of silo. Okay, it will act at the bottom. When it is acting at the bottom, it is PL, PV. Okay, because it is vertical in direction. When it is acting horizontally, like this, okay, like in this two direction, then it is lateral pressure, and when it is vertically downwards, then it is vertical pressure. So we will design for vertical pressure and lateral pressure. So we have seen that there are some specific terms. Okay, those terms we have learned, but where we will use those terms? You will see here that when we are going to design a smooth wall silo, very smooth wall silo, at that time we will see where either we are going to design for lateral pressure or vertical pressure. At that time we will keep our bulk density maximum. We will take the maximum value of bulk density for our material, and angle of internal friction will be maximum. The maximum value of angle of friction we will take, whereas at the same time we will take the minimum value of angle of friction of grain with walls, like what it is external friction. Okay, so when we are going to make rough wall silo, we have seen the rough wall silo or corrugated steel silo. Okay, so in that case, when we are measuring the lateral pressure of inside the grain, we will see we will take the minimum value of bulk density and minimum value of angle of internal friction and minimum value of angle of external friction. Okay, whereas when we are designing for the vertical pressure, at that time we will take the maximum value of bulk density, maximum value of internal angle of friction, and minimum value of external angle of friction. Okay, so from this you will get might have got the idea where we are going to use the properties and how we should use the properties when we are going to design the silo. Okay, so then after this there are some grain theories. Based on that principles, we will design the pressure vessel. Oh, sorry, the storage tank. Okay, what are the those grain theories? So first one, how this grain theory started. So basically, this grain theory, first grain theory started. Grain pressure theory is started that we consider the grains as a semi-liquid component. Okay, so we will consider the grain as a liquid, not as a solid. Okay, and then whatever the density of this grain is there, we will shift this density to the this liquid, and then we design for liquid. Why we took liquid? Okay, why we are not taking grains? So there is one property of grain. Okay, that the pressure inside, there is a property of liquid. Okay, the pressure inside a liquid is equally distributed throughout the surface. Okay, so here if I draw, sorry, So if I draw here, if it is a liquid, then pressure here, acting here, okay, at any point will be equal. Okay, there will be no difference in pressure. That's why we consider it as liquid. Whereas when we store grains, it makes heap. Correct. When we are storing grains, it will not be straight. It will make heap. So because of this heap, the pressure will be more here and less here. At that time, the designing of silo will be very difficult. Okay, so we consider this this grain as a liquid, and we assume that pressure is distributed equally inside the storage tank. Now, then we used this equation, okay, to find out the lateral pressure inside the storage tank. So where PL is the lateral pressure, W is the density of grain in kg per meter cube, and H is the depth of the grain from the top. Like this will be the H. W will be the density of grains, H will be the height. So this was the basic pressure theory. But we need to, like I have told you, that we considered solid as a liquid, and this is not the case. Okay, because pressure will be different. And when we started designing on that previous theory, we found that lot of silos got failed because of that theory. Then we need to modify that theory, right? So Mr. Rankin, a great scientist, modified that theory and added one coefficient, Rankine coefficient, okay, denoted by K. So what is this Rankine coefficient? This is equals to 1 minus sine theta 1 plus, sorry, sine phi 1 plus sine phi, where phi is angle of internal friction of grain. Okay, they consider some angle of internal friction of grain, and they find out this angle of internal friction of grain has to do something with the pressure. And then Rankine's equation. From this equation, we found out that structure was little bit better, but still not sufficient. Okay, because there are various type of silos. Okay, there are deep bins, deep silos, or shallow silos. Okay, so what do you mean by deep silo or shallow silo? Okay, so suppose this is a silo in which grain has filled, and what happens when we have filled the grain? There is there is plane of rupture. Okay, there is plane of rupture. This plane of rupture is the line from which that grain will start flowing. Like this grains will start flowing when this structure fails. Okay, so this grain is having some angle, okay, which will start flowing in this direction, whereas this bulb will having force in bottom. Okay, they are acting their force towards the bottom, but whereas this one is having some angle. So the line which is separating those two force components are the plane of rupture. Okay, so how we define deep shallow or shallow bin or deep bin? So again, this is field of grain. So again, this is plane of rupture. Plane of rupture. So in case of shallow bin, the plane of rupture will touch the top of grains before crossing it. Okay, the top of grains it will touch, whereas in deep bin, the plane of rupture will touch the opposite wall before crossing the grains. Okay, so both the ends will touch the opposite ends. Okay, of plane of rupture will touch the opposite end of the silo. Whereas in case of shallow bin, it will touch the top of the grains and one ball. Okay, this is the difference between shallow bin and deep bin. So these are the equation which we used for designing of deep bin, lateral pressure of deep bin and silo bin, where PL is the lateral pressure, W is the grain bulk density, H is the height or depth of the grain, and this mu, as we already know, mu is the coefficient of friction, and mu dash is the tan theta, okay, which is the mu is the coefficient of internal friction and mu dash is the coefficient of external friction. Okay, so next is Janssen formula. Janssen formula is for deep bin. So again here PL is the lateral pressure and W is the grain bulk density. R is the hydraulic radius of the grain. Okay, hydraulic radius of the silo. Mu is again coefficient of friction. E is exponential and K is the constant. Mu is again coefficient of friction. H is the depth of grain at which we are going to find out. R is the hydraulic radius again. So based on these two formulas, we are going to solve some numericals. So here in this numerical, first numerical is about design of shallow bin. Okay, so in this we will use Aries formula. So Aries formula we have seen here. Here we know in numerical we know what is W, what is H, what is mu. Like we are having both the sorry, let me change the pointer. So we are having both the angles. Okay, internal friction angle and concrete external with wall. What is the angle? Okay, so we are having tan phi. This will tan phi for external. This is tan phi for internal. Put into the formula, get mu and mu dash, and then you can solve this numerical. Okay, remaining everything is given. W is given. Okay, H is also given, and R is also given, and you don't need anything else. In this will be the Aries formula. Okay, just here also everything is given. Put the values in equation, and you will get the answer. Okay, thank you, and this is it for today's lecture. Next lecture is about design of autoclaves, in which we will design some sterilizer and autoclave